So next, let's get it started. We have a Stella from NOD/AMD.
Yeah. Hi, folks. This slide is out of date. Like last week, I finally got a NOD AI t-shirt the day before we announced we were getting acquired. So I wore it around and said it's fine. But for those of you who don't know, Stella, founder of the Erie project, and formerly worked at Google, then at NOD AI, and then working on AMD acquisition here. So wanted to jump in and caveat that I'm going to make this short and sweet because some things didn't line up how we meant them to. The original talk of this deck was going to be all of the amazing things we were doing with i4 inference on Llama, on CPUs and other hardware, but we weren't quite ready to share those numbers yet. It's looking good on micro benchmarks, but wasn't quite end to end where we wanted. So instead, I was going to focus on giving a brief talk on some of the technology that we were putting into that, because the team has been working for a number of months on basically trying to get the top line numbers of inference cases for the large language models through the Erie compiler, and being competitive and beating Llama CPP, and that's involved a lot of low-level compiler optimizations, data tiling, microkernels, and a lot of quantization and work in PyTorch to be able to get I4 models out. So I'll just be talking about a piece of that here, and also just wanted to say too, give a thanks to Google for hosting the Erie project and OpenXLA and paying our CI tab. That's really helpful, and we really appreciate it. And also further caveat, this was supposed to have been given by someone else, and this was their talk, so forgive me if I stumble a little bit. So what is Erie? It's a compiler stack, built on MLIR. It was one of the earlier ones that we actually built it. Started building it before MLIR was published, and it's since grown multiple input types, for different frameworks, and executes on different backends, and it slices and dices and makes tea and all that stuff. So what we were trying to do with this work, like I mentioned, was improving the performance of generated code, especially for CPU backends. And the motivation, again, we were really chasing inference workloads, getting the right instruction schedules, avoiding stalls, optimizing register usage, all the normal stuff, and doing that in a somewhat systematic and scalable way. Let's see. In this work, we coupled two things together. One is that Erie provides a workflow that lets us call out to libraries and integrate those with the runtime at the top level, so you can basically do library replacement and at a very coarse-grained pattern match and replace in some fashion. What was or historically it could do pure code generation with MLIR through Linao vector dialect, the alphabet soup of MLIR code generation technologies. And what we like about the code generation technologies is that they are dependency free. They let you theoretically code it once and reap the rewards multiple times, all that stuff. The advantage to libraries, of course, is you get tight control. You get very tight. It's much cheaper to get tight control. You can do everything in both, but it's a lot cheaper, and you get to write in C and do some other things. So we were aiming for a what if there's the best of both worlds, and we started bottom up and said, what's the smallest atomic unit with an optimal instruction sequence? We started with basically saying, especially on CPUs, getting the block level instruction sequence right is often the difference between top tier performance and 60, 70, 80%. And we had had folks in our team, including some of the original Eigen authors, some of the original TF Lite authors, who are just writing kernels can write kernels in their sleep. So we decided to just mash these two worlds together and see what would happen. And then we'll give a brief interlude if anyone here doesn't know what matrix multiplication is yet. Here it is in pictures. I'm going to skip through this. We all know what tiled matmuls are. The other thing that we added in this work was representing data layout and ordering in MLIR. Typically you're starting with with, let's call it a matmul, and you've got your tensors. They're dynamically shaped. We introduce packing around this and pack the inputs. Then do a translation, usually to a better tiled form. These are all high-level transformations that happen at the tensor level in the compiler, and then we unpack, and these basically become peephole optimizations for doing local data layout transformations, and with the main goal of translating to some higher dimensional compute operations that are easier to do multi-level tiling on and whatnot. And then the other trick that gets done, which isn't particularly novel, you just do it, is that once you've established your ideal layouts, on your hero areas of your graph, is you propagate them. You propagate your packs and unpacks to the edges as much as possible. You break ties. You do these other things, and then that lets you fuse the packs and unpacks with consumers and basically start to get them for free. Then to pull it further together, now that we've got the fusions in nicely tiled forms and complete with their data layout, we can generically code generate those through LLVM's code generation infrastructure. We can get all that going, but we also support an IR-driven offload to microkernels, which basically is just a compile time. We have a library of C code that is very we'll have a generic version and a very usually intrinsic heavy or inline ASM version that when we're building the compiler, we build that to bitcode and then inline it dynamically at compile time. So this isn't actually introducing library dependencies, but it's letting you write in a very library-like form for your high performance sections of the kernels that you care about, because you're just writing C code. And so then that gives you the development flow is a lot more improved, because even though the compiler is integrating the bitcode streams and doing LTO and whole program optimization on that, you as a library author are just iterating on C code on the side. You're running your usual micro benchmarking, you're getting your instruction sequences right, you're doing all that stuff. So we found that for when you've got to specialize these cases, that's just a much better development flow to be working on. And then you can easily specialize to other architectures. All of this interops with the usual, if you're familiar with MLIR code generation techniques of moving from tensors to buffers and bufferization and all that jazz. And then it induces a calling convention that you match up in the C code that you've embedded in the compiler. So putting it all together, we pack the operands, we tile the outer tile coarsely at the whole program level, converting the relevant DAGs to these U-kernel ops that the compiler can LTO optimize together, and then bufferize and lower to function calls. And the main thing that we did out of this, other than development velocity for letting library writers effectively work in their native domain while also getting fusability and other composability aspects that you usually get from a compiler, is deployment. There's no external implementation, It implements, it integrates at the LLVM-IR level. There's some other tricks that we do to make sure that all folds away. It lets us write very switchy and branchy kernels that you would never usually do in a classic runtime, because we inject globals in there that control for the target environment, and the compiler folds it all away, never gets run. So what we found is it's a very convenient way to author, just pretty branchy C code and have it do the right thing. In practice, this works pretty well. The space is always moving, so I think these numbers were current as of a few weeks ago. A few months ago, they were a lot better, more in favor of Erie, but everyone's moving forward. So basically, we're in the ballpark on many of these. With some of the normal matmul heavy workloads, being right around where they should be. On some variants of mobile devices and ARM CPUs, and especially those that are going to have instruction cache pressure and other cache pressure, the performance can be quite exaggerated by actually letting the compiler take another swipe at what amounts to interloop library code. And at least in our benchmarking, the memory usage was a lot better than at least this canonical example of a well-baked runtime or library heavy runtime for some workloads. End-to-end performance, again, some of this we don't have all the optimizations implemented yet, but Erie is ahead of some of the classic implementations, behind on some stuff, but we're in the ballpark. And at this one in particular, we've been working on for a long time to really follow the great work that the GGML folks have been doing in blazing a trail and basically saying, what's the how can we get performance without the fluff, and then teaching the compiler to do that. And this is we're getting pretty close on that. In fact, the micro benchmarks that we weren't showing, we're matching GGML for inference of asymmetric quantized llamas, and but then there's some whole model things that are causing some extra mem copies, and it slows it down by 10 or 20%, and that's being fixed. Next up, we're working on enabling all of this right now, addressing some low-hanging fruit, expanding it to more of the code generation pipelines, especially for inference. A lot of these LLMs are very mat-vec and vec-mat heavy, and those show up a lot more frequently than they do in training or more classic models. So just has gotten a lot less attention. We'll be focusing on that. And then we'll be expanding the microkernel support from being kind of a prototype on a small set of code generation pipelines to being able to support any of the contraction op interfaces. That gives us much more mixed precision support and all of that. And then longer term, pushing this to allow these offload to these library or these not libraries, compile time libraries out of tree. And I believe the rest of this was not slides that are relevant. So that's the basic talk on kind of a view of the world on what a part of the Erie team has been working on for the last few months to really chase the top line inference numbers.